Hello, Math 101 students from Hazleton County Community College. This is Justin Kushar here. This video I put together focuses on section 5.3 from your lecture notes. Chapter 5 is all about number theory, and tonight I'm just going to do one section 5.3. In an upcoming video I'll handle section 5.4. I've already got several questions. I'm glad you're reading the material, so hopefully this will clear things up for you a little bit. On a side note, I hope everybody's staying healthy and well in mind and spirit. And again, if you have any questions, please feel free to reach out and ask. I have no problem answering any of your questions. I would ask you to do so predominantly more towards the evening, because on my other teaching job, I have office hours during the day, and I want to be able to devote time for it. So if you could ask questions in the evening hours, that would be great. But section 5.3 in your textbook is selected topics from number theory. So far in chapter 5, we've been learning about exclusively one set of numbers, which is the natural numbers. And we like that set of numbers because the natural numbers are just the counting numbers, 1, 2, and 3. We certainly like those types of numbers because they're not fractions, they're not decimals. But in this section, we start to go a little bit more deeper in terms of the natural numbers. So to get started, you have to understand this definition here, what a proper divisor is. And in your notes, a proper divisor is all divisors of a natural number except the number itself. So for example, if we look at the number 4, 4 would have proper divisors of 1 and 2. We don't count 4. If you look at the number 2, for example, 2 only has a proper divisor of 1. That's it. It's kind of short-changed if you want to think of it that way. So we have to understand that because the definition of a proper divisor carries us through these special types of natural numbers. So we have what we call a perfect number, an abundant number, and a deficient number, okay? Now, those are all types of natural numbers. So they are, you could think of it as a subset of the natural numbers, these special types of numbers. And there's actually many more than just these types. If you look in your textbook, they'll talk about weird numbers and amicable numbers. But these are the only two we're going to focus on. So what exactly is a perfect number? Well, a perfect number is a number where it is equal to the sum of its proper divisors. So the example that I gave in the notes that we'll look at here is the number 6. 6 is considered a perfect number because the proper divisors of 6 are 1, 2, and 3. And if we go ahead and add up those proper divisors, 1 plus 2 plus 3, that gives us 6. And 6 is certainly equal to 6, so that's how we know that number is perfect. 6, by the way, is the least of all the perfect numbers, and to this day, we don't know how many perfect numbers there actually are. There could be quite a bit more than we think, but it's something that hasn't been solved quite yet. Now, another type of natural number is what we call an abundant number, and by definition, an abundant number is less than the sum of its proper divisors, right? So the example I gave you was 12, and let's check it out. We're going to claim that 12 is considered an abundant number. The proper divisors of 12 would be 1, 2, 3, 4, and 6. Remember, we can't use 12. So if we sum up these numbers, and I'm going to do that a lot. I'm going to break a lot of chalk because I write pretty heavy. If we add up these numbers, 1 and 2 is 3, and 3 is 6, 6 and 4 is 10, and 10 more is 16. So 12 is clearly less than 16, so 12 would be considered an abundant number. Okay? And then finally, we have what we call deficient numbers. And deficient numbers are numbers that are greater than the sum of its proper divisors. And there's quite a bit of deficient numbers out there. And we'll take a look at one whole classification of actually deficient numbers. But for example, in your notes, I gave you the number 8. We claim 8 is a deficient number. Now let's check it out. Again, your first step is consider what are the proper divisors. Well, the proper divisors of 8 would be 1, 2, and 4. And if we add up 1, 2, and 4, that gives us 7 on a normal day. And 8 is clearly greater than 7. So that's how we know the number 8 is deficient. Okay, so we have perfect, abundant, and deficient numbers. Again, I would encourage you to pause the video at this point if you need to go back and be familiar with these three special numbers. Okay, so what I'm going to do at this point is I'm going to give you a list of numbers, and I'm going to have you at home, wherever you are, work on determining if the following numbers are perfect, abundant, or deficient. By the way, I made this chalkboard myself, 3 coats of Rust-Oleum chalkboard paint. You have to have a smooth wall. Let me know what you think, if you're able to see the board clearly in your video or not. So we're going to classify as perfect, abundant, or deficient. Now let's take a look at numbers I have for you. So we'll do 18, 2, 6, 3, 40, 19, 284, 28, 31, and 17. So what I'd like you to do is go ahead and tell me, are these numbers either perfect, abundant, or deficient? So now is a good time to pause this video, go ahead, figure it out, and we'll come back and discuss it. Okay, hopefully you had enough time to figure these out. So let's go through the answers here. The number 18 would be abundant. The number 2 is deficient. Number 6 is perfect. Number 3 is deficient. The number 40 is abundant. The number 19 is deficient. 284 is actually deficient. 28 is perfect. 31 is deficient. And 17 is deficient. So I hope that you got these answers. Again, the key is making sure you understand the definition of what a proper divisor is, and then the second step is understanding the definition of what a perfect, abundant, and deficient number is. Again, if you have any additional questions on these, please feel free to give me a call or text or an email, and I'll walk you through some more examples. If we look at this list of numbers here, look at some of the numbers that turned out to be deficient, for example. The number 2, the number 3, 19, 284, 31, and 17. Now, with the exception of the number 284, there's something interesting here that you should take from this, is the fact that 2, 3, 19, 17, 31, they are, do you know what kind of numbers? I'm hoping you know. Prime numbers. So all these ones that were prime turned out to be deficient. So we have a theorem that says all prime numbers are deficient. And that is a theorem. So that is something that was proven. So all prime numbers are deficient, okay? However, the converse of this is not always true. So not all deficient numbers are prime. And here's a perfect example. 284 is a deficient number, but this is clearly not prime. As you know from the previous section, you should know that this is at least divisible by 2, so it's definitely a composite number. So all prime numbers are deficient, but not all deficient numbers are prime. And that's a huge implication. I hope you'll be able to take that with you through the rest of this course. Okay, so again, any questions, please feel free to call, email, text. I'll get back to you as soon as I could. And we have one more thing we have to talk about briefly here, and that will be the end for this lecture. I bet you wish all the lectures in class were this short, right? That'd be pretty nice. Take a 3-hour class down in 15 minutes. There's one thing that you should have read in your textbook. A mathematician named Christian Goldbach. Now, Christian Goldbach was born in 1690 and he died in 1764. So again, in terms of mathematics, not all that long ago, really, right? Not all that long ago. Again, we often think of mathematics as a really, really long time, like the Greeks and the Babylonians and the Egyptians, but again, a lot of good stuff done mathematically, not so in the distant past. But Christian Goldbach had this conjecture, and this conjecture is still not even proven today in 2020. So mathematicians are able to do a lot of things, but this is one thing they were not able to prove quite yet. And his conjecture says that every even number greater than 2 can be written as a sum of 2 prime numbers. So every even so sometimes we use the capital E to represent the set of even numbers. So every even number greater than 2 can be written as a sum of 2 prime numbers. And this isn't all that difficult to think about if you really think of it. You've been doing this for a long time. In fact, in elementary school, this is something that you usually have done in like different activities when you're learning about number sense and that. But we could take any even number he claimed, and its sum could be written as 2 prime numbers. So we'll look at a few examples. So here's an even number, 8. See, I told you I'd be breaking chalk left and right. Here's an even number, 8. And we can write this thing as the sum of 2 prime numbers. And this is a quite easy one because it's a small number. We can write 8 as 5 plus 3. Right? We can write it as 5 plus 3. These are 2 prime numbers. We can't say 7 and 1 though, because 7 is prime, but 1, remember, is classified as neither prime nor composite. So we can't use that. Sometimes there's more than one way of writing it. We can't say 6 and 2 because 6 is not prime. So this is pretty much it. However, for example, a number like 10, this one isn't so bad. Most of you will think of 5 plus 5 as 10. These are 2 prime numbers. How about what else? Is there any other examples you could think of? How about 7 plus 3? Both 7 and 3 are prime numbers. They add up to 10. Another example would be 24. 24 could be written as 21 plus 3. But it could also be written as 19 plus 5, for example. And perhaps you could find some other combinations too that would work out for you. So this is a conjecture from Christian Goldbach, meaning that, as you know from the course, the conjecture is something that has not been proven or disproven yet. These would be examples that would lean towards saying that he's correct, but we don't know for sure. There's no hard proof. So with that being said, that's the end of section 5.3. So perfect abundant deficient numbers and gold box conjecture. So hopefully I help you with some of your exercises in the text. Tomorrow I will do another video for you on section 5.4, which is greatest common factor and least common multiple. So until then, stay safe, stay healthy, and I'll see you when I see you.